Today, we'll be looking at the binomial theorem. It does include some HL-only parts, but we'll tell you when those are. You've probably expanded things like a plus b squared, or maybe even a plus b cubed before. Notice a pattern in the powers? For a plus b to the n, the powers of a decreases from n down to 0, while the powers of b increase from 0 up to n. So the sum of the powers in each term is always n. But what about those coefficients? 1, 2, 1 for n equals 2, 1, 3, 3, 1 for n equals 3. You may have encountered Pascal's triangle before, in which case you should recognize this pattern. Each number is the sum of the two directly above it. This triangle gives us the coefficient for expanding a plus b to the n for small positive integer values of n. While Pascal's triangle is neat, it's not practical for large n. So, we need a more direct formula. This is where combinations come in. This tells us the number of ways to choose r items from a set of n items. Turns out, these are exactly the coefficients we need. So, the binomial theorem for a positive integer n states the following. Or, using sigma notation, which we saw in our sequences and series video, remember NCR equals r factorial divided by n minus r factorial times n factorial, where n factorial is n times n minus 1 times n minus 2, etc., all the way to 1. This formula is in your formula booklet, but understanding where it comes from is helpful. Think about expanding a plus b to the n, so that's a plus b times a plus b, etc. Then, to get a term like a to the n minus r times b to the r, you need to choose b from exactly r of the n brackets, and a from the remaining n minus r brackets. The number of ways to choose those r brackets is precisely n choose r. We're now going to move on to additional HL parts, so if you're SL, that's all you need to know. We've dealt with positive integers, but what if n isn't a positive integer? What if it's a negative or a fraction? This might seem strange, but it's actually incredibly useful, especially for approximations in calculus and physics. The standard formula for n choose r with factorials only works if n is a non-negative integer and r is inferior or equal to n. So we need a more general definition. We can rewrite n choose r, which is equal to r factorial, over n times n minus 1 times n minus 2, etc., multiplied by n minus r plus 1. This version works even when n is not a positive integer. Using this generalized coefficient, we can extend the binomial theorem. The expansion typically uses the form 1 plus x to the n, because any a plus b to the n can be written as an 1 plus b over a to the n, and we can apply the theorem to the 1 plus b over a to the n part. For any real number n, positive, negative, or fractional, the expansion is the following. And, using our generalized coefficient notation, notice something crucial. This is an infinite series. Unlike the case for positive integers n, this series doesn't stop. Now, as we discussed in the relevant video, infinite series don't always converge to a finite value. For this binomial expansion to be valid and useful, the series must converge. This happens only when the absolute value of x is less than 1. Intuitively, if the absolute value of x is less than 1, the highest powers, x squared, x cubed, get smaller and smaller, allowing the sum to approach a specific value. If the absolute value of x is bigger than 1, the term generally don't shrink, and the sum diverges. So, when you're asked to expand something like 1 minus 2x to the 1/2, or 1 plus x to the minus 1, you use this generalized formula. Calculate the first few terms, using n choose r, and state the conditions for validity. In these examples, the absolute value of minus 2x is smaller than 1, so the absolute value of x is smaller than 1/2, and the absolute value of x is smaller than 1, respectively. The binomial theorem pops up a lot in probability, in calculus, for approximations, and in general algebraic manipulation. Getting comfortable with both forms, and especially the validity condition for the infinite series, is key. That's the essence of the binomial theorem. Next time, we'll be looking at quite a complex unit. See you then.